Well, this is Geometry Chapter 5.3. This is the second part of bisectors and triangles. We're going to focus on angle bisectors. We're covering these topics. First thing we need to do is to review what an angle bisector is. An angle bisector is going to be this line, or ray, starting from the vertex at point A, and it goes through point G, and it extends infinitely, and it cuts this angle, angle CAB, in half, so that this angle over here is congruent to that angle over there. And see, I have two tick marks there, two tick marks there. They don't line up, so this way you're not confused about whether or not we're talking about all of this angle, or this little part over here and that little part over there. This little part here is congruent to that little part there, which is illustrated here. Okay, the big thing that we get to learn now is that any point that is on that angle bisector, right there, there's a point that's on the angle bisector, is equidistant from the sides of the angle. And the way we measure that equidistance is that we have this common point, and then you extend a line segment to the ray, the side of the angle, and it has to intersect that ray at a right angle. And likewise for this one as well. And once that is achieved, then this is equal in distance as this. Let's have a video to show this. So here's a video. Let me try to start it. No, it's being a pain. Let's try again. No. There it goes. So when we slide that point up and down the angle bisector, you will see that it is always equidistant from the sides. Okay, so let's move on. Okay, now we have the concurrency and angle bisectors theorem, and that's just saying that if you draw an angle bisector from each angle of the triangle, here's another one, and there's another one, where they meet, that point of concurrency, we're going to refer to that as the incenter, and then once you have that incenter, let me see if the next frame shows it. Yes, it does. Then you have that incenter, then it means that you can draw a circle that is equidistant from the sides of the triangle. Okay, so this radius of the circle is obviously the same length as that radius, that radius. All these statements here are basically saying that we have angle bisectors. And then we're saying that we have congruence from that point of concurrency, the incenter, to the sides of the triangle. That's what's going on here. And then we're specifying that when we make that measurement, that each of these radii of the circle that's inscribed inside the triangle, that they intersect the sides of the triangle at a right angle. Okay. It's covered there. Let's keep going. So I made a video. Let's see if it plays. Oh, it did automatically play. And you can see me drag point G around, and you'll see that the circle that's inscribed inside that triangle, it's always inside it, never goes outside it. The incenter, point G, always inside that triangle, never goes outside it. Pretty much it. Let me pause it for a second. You'll notice that no matter how this point drags around, see, this angle is congruent to that one. This one is congruent to that one. This one is congruent to that one. No matter how I drag point G around, we are always dealing with angle bisectors. Now, let's extend this line. If I extend that down, you will see that the ray BG, when it intersects that side of the triangle, see, it's certainly not a midpoint. It can be, but it doesn't have to be. Let's continue on this video. Nope. See, right about there it would be a midpoint, but that would be a special case. It would have been an isosceles triangle. Visually, I don't. Okay, let's keep going. Now, I drew 3 quick examples of this. I have an acute triangle, and see, you can see the angle bisectors. and then you can see the point of concurrency, the incenter, and you can see that a circle can be drawn that just barely touches each side of the triangle. Its tangent touches at only one point. Here's the same example, except for it's a right triangle, and here's it's obtuse. Now let's apply what we've learned. If we specify that DG is 3, so I'll draw a little 3 right here, and EG is x over 5. I'll put a little arrow to it, but that's x over 5. And if we say that BD is 4, well, which of these pieces of information can we set equal to each other? Well, the ones that we can set equal to each other is that and that, because those are the radii of the circle that's inscribed in that triangle. So, going back to there, our concurrency of Angle Bisectors theorem, that the point of concurrency is equidistant from the sides. So let's go back to our problem. There we go. So that means we set DG is equal to EG. I think I have the math already written out. Let's slide that rectangle down and see. Yep, I set those two line segments equal to each other, their lengths, and then there's the substitution of those expressions in its place. Multiply both sides by 5, x is 15. And that's it. Thank you for watching this video.